Okay. Good morning, good afternoon, good evening, everyone. Thank you all for joining. Hope you had a good week. Um, my name is Karan Bazirani, and I am the Technical Performance Specialist at Udacity, and I manage the School of Business in particular. I have been in the Udacity ecosystem for 7 years now. I started out as a project reviewer, and then in 2021, I transitioned into my current full-time role. And what we have today is our final session for the deep dive webinar pilot. This particular initiative will be a recurring feature in 2025, but this is the last slated session that was a part of our initial pilot. And joining us today on this call is Ayushi Jain. Ayushi is a colleague from my team, and Ayushi oversees operations at Udacity for School of AI and for School of Programming. Thanks for being here, Ayushi. Now, actually, it's time to introduce the star of the show. And it's a pleasure to introduce Ahmed. Ahmed is a research assistant and a PhD candidate, and he's been a mentor at Udacity since 2018, and he's completed close to 3,000 project reviews. He specializes in GPGPU programming and high performance computing, and his research focuses on enhancing SPH simulations to advanced parallel computing techniques. Now, before I hand over the floor to Ahmed, just a couple of quick points. The first would be that this webinar will be recorded. And the second would be, I would request you all to use the Q&A tab if you have any questions. Please feel free to post your questions there. We have a section dedicated towards the end of the call where we'll take up all your queries. And with that, the floor is all yours, Ahmed. Let's get started.
Thank you so much for the introduction and welcome to the webinar. Let me share my screen. So today we're gonna have a webinar about developing your mechanical simulation program, or in other words, you will learn what is happening behind the scene for mechanical simulation programs. But let me introduce myself first. I'm Ahmed Elbossily. I'm working for Udacity for more than 5 years. I graduated and worked as a land system engineer, had my master's degree in computational mechanics. After that, I moved to work in R&D, and I'm a candidate, Ph.D. candidate at Leuphana University. So my research focus in GPGPU programming, and more specifically in enhancing simulation program and make it work on GPU and speed it up. So what we will learn today. So we will begin with what is the prerequisite to understand what is going on in this presentation. And we're gonna have overview about mechanical simulation, what is available tools in the market, what is happening there, and why you should learn this topic, and what we will focus specifically today. After that, we're gonna move to the problem itself and define the problem and build our code. We're gonna start from scratch, and at the end, you will have a program compared to the commercial programs available in the market that can do the work. So what is the basic requirement? So you need to have a basic, we're gonna use a C++ language, and you need to know the basics of it. And if you don't know the basic of C++, any programming language, it should be enough. And what tools we will use? We will use Linux operating system, G++ compiler, Visual Studio Code, ParaView, and all these tools are open source. So this is the advantage. Okay, so mechanical simulation program. If you made a quick search about mechanical simulation programs available in the market, or if you came from a mechanical background, you will know that we have something called the Autodesk Inventor, Abacus, ANSYS, OpenFOAM, and there are some others. These are joint like companies are controlling this market, and they are specifically working in simulation mechanical processes or mechanical phenomena like bending, what's happening inside the engine, what is going on around the turbine, and the flow. All these like phenomena can be simulated using like any of these programs. And why we need that? Because simply we need to understand what is happening inside these processes, and we don't need to go to the lab every time, so waste the time, money, effort, so we can do it on computer. So this is the idea of mechanical simulation programs. So why you may need to learn it? So first thing, if you are working in a research field, yes, we have very good available tools in the market, but these tools are not open source. What does it mean in open source? It is a closed solution. You don't know what is happening behind the scene, and you can't modify it. And sometimes you need to do some modifications that is not you are not allowed to do it. So if you wanted to study a new case, if you found something in the laboratory, like new phenomena, and you wanted to apply it, you can't do it because it is a closed, not open source programs. It is closed. You can just use the interface and you can't access what is behind the scene. So this is the first like reason if you are coming from a research field. And the second reason you may need to learn it is job opportunity. So these like joint companies is looking forward to good programmers and good guys knew the theory. So if you can combine both of them, you own the world. Actually, you can have like a very easy job opportunity for these companies. And last thing, it is kind of progress. Like now you understand, okay, now everyone knows like what is the idea of machine learning and what is happening behind the scene. Also, this is, you can learn what is happening behind the scene regarding simulation programs. So how it works regarding mechanical simulation programs. So you may have a thermal problem, like a thermal problem, like if you like when you was a child playing with your PC and you open it up, you will have like a heat sink that like takes the heat away from the processor. So this is a thermal problem, and we need to design and design as good fins that able to take the heat away from the system. So this is called a thermal problem or a mechanical problem, like if you have bending for a cantilever beam or bending in any structure. So this is a mechanical or deformation problem, or maybe you have a thermomechanical, like friction, like a roller that rolls over a surface. So this is called thermomechanical because we have heat generated due to friction, and also we have like mechanical stresses. So this almost the problem in mechanicals. And we have another category about like CFD, like computational fluid dynamics. This is also considered with us. So how we can solve this problem? So you can see to the left, it is what you see, it is a continuous domain. So to computers, we need to digitalize it or convert it to discretization or points. This can be done by regular mesh that like you can see. So we can solve the problem at the point of intersections that you can see it now, or maybe a regular mesh like this one. So at every intersection, we can like solve the equations that control the system. And the last one, we can even use points, just points. So how we can solve the equations that describe this system. And luckily, like for the thermal and the mechanical and the thermomechanical, there are exist equations that can describe the system. So we can use the differential equation and solve it, so we can have the results across like over the time. So we can solve it using finite difference, finite element, or smooth particle hydrodynamics. So we can solve the system or the governing equations. And finally, you will have the result, and the results are just numbers, and we need to visualize it. So we can visualize it using a matplot library or maybe VTK file using ParaView. Like these are just tools for visualization. So what you are seeing here, it is what is happening in like commercial programs. They are doing like that. They have a problem, discretize, solve, and visualize, and all these packages are in just one place. So we're gonna go through these steps like that. Like today, we will focus on a thermal problem, and we're gonna use points or particles. And we're gonna use the smooth particle hydrodynamics to solve the equation, the heat equation that describes the system. And we're gonna use ParaView, which is an open source program to visualize, okay, the temperatures in a 3D form. So before going any further, I mentioned that we're gonna use the SPH. So let me just have a quick, you should. Okay, so we have a quick, what is the SPH, or what is your information about the SPH? What is the advantage of it? So I may launch a quick quiz or poll, but it is not here. So anyway, we can move on, no problem. So what is the advantage of the SPH? It can handle a large deformation
I've
or
launched the
require.
quiz, Ahmed.
Yeah, thank you. So if you know anything about smooth particle hydrodynamics, you can choose one of the three choices. What is the advantage of using it? A, can handle larger deformation, or B, require low computational power, or C, can't handle multi-physics. So what do you think? Okay, so I think you know a lot about SPH. Okay. So yes, most of you like choose the first thing. It can handle large deformations, and it can be like perfectly represent the deformation of the deformable bodies. So this is the advantage of it. Require a low computational power? No, this is not. This is actually SPH. The theory behind it exists like more than 15 years ago, but due to it require a lot of computational power, so it is limited in use. But now with the availability with HPCs and GPU programming, it can be applied easily, and it has a good results compared with other methods. So can't handle multi-physics? No, it can handle multi-physics perfectly. So the advantage is that it can handle large deformations. Okay. So let's have a problem and try to solve it by developing the programs that can show us the results and at the end. So for example, our example today is about if you have a cube just 10 by 10 by 10 centimeters, and you have like the initial temperature on one face, like maybe this is the temperature of the processor. And I wanted to know what is the temperature at the end, or the distribution of the temperature inside this cube after 10 seconds. Like maybe what is the temperature here? What is the temperature like over the domain? How can we do that? So again, let's recap what we discussed. So we have a problem. We will discretize it into points, as you can see. After that, what we will do, we will solve the differential equation that is representing the heat interaction, or heat equation, or heat transformation from particles to one to another. And this equation, it exists in literature. Like you can search for heat equation and you will find it. And this is just adjusted for smooth particle hydrodynamics. So we're gonna, as you can see, it says that the change of any particle I over like the change it over the time. That is why we have dot. It is a function of the temperature of this particle, Ti, and the particles around it. So this is just a simple equation. Like the temperature of the particle is depend on the surrounding, and we multiplied it by just weight. This gradient just weight, like if a particle is far away from this particle of interest, we will give it a low weight. If it is close, we will give it high weight. So this is partial differential equation. It's so simple that like the temperature, change in temperature over time, it depends on the temperature of the surrounding. And finally, after 10 seconds, we can have the final results, like the temperature distribution. So yes, so that's it. So let's go and dive into our code, our programs that we will develop that solve this problem. So from where we will start, we will go one step back, actually. We will start, okay, what is data type we wanted to use? So here we will use a GLM library. GLM library, it is open source library that can handle matrix and vectors multiplication very easily. And like, because we are like dealing with 3D, so we will need 3D point X, Y, Z. So we need a data type of that can hold a vector. And later we may use matrices, so it can be easily handled. So this is the first thing. What else? We're gonna use something called use double precision or use single precision. In mechanical simulation program, we need to specify, okay, do I need very precise results, like double, like 0.000 to 17 digits after the mark? So do we need this precision, double precision or single precision? And based on what you want, it's gonna strong affect your results. So if you want more accurate results, you will enable like this part by defining use double. So now we are using the double, and this is the double will gonna be used as a float underscore t. So if I commented this line, so in that case, it will go to the else. And in this case, float underscore t, it's gonna represent it by float. So by doing this hack, okay, I can use only float underscore t as my data type. And in this file, if I defined use double, so yes, now I'm using a double precision. If I defined not like comment this line, so it will go to the else. So I'm using single precision. And double and single precision, it affects for the performance, like it can speed up your program or slow it down, and the accuracy. So it is something the user need to decide. So this is the first thing we began. So the first thing we need to ask ourselves, okay, what is data type we will use, and what is the libraries that are gonna help us through the upcoming code. What else? So, okay, so for every particle, we need to get some information about every particle in the domain. So we created a structure or a class. So the structure or a class will hold the information for us. So what information I need? So first I need the position, like these particles, every particle has its position, X, Y, Z direction. So the first thing, I need a position. The second thing, I need like from the equation, I need the temperature for every particle. I need something called thermal conductivity. I need something called density. I need something called specific heat, and the change of the temperature for this particle. So all this information, we need it. It is a material property. Like every material property, every material has its own density, has something called thermal conductivity, has something called specific heat. So this is something related to the material itself. So we need to gather this information over the time. So maybe this property changes over the time, or maybe constant, but at least we need to have it. So what you can see in this equation have two other parameters represented by, okay, if you have a friction, if you have heat generated due to plastic deformation, but we assume, okay, we don't have a friction, it is just thermal problem. We don't have a friction, we don't have a plastic deformation that generated heat. So we're gonna neglect these two parameters. So you can see here, like we are now in the particles.h file. So let's go to the particles.cpp file. And here we define in the class constructor, we're gonna allocate memory in the heap. We usually, for these kind of programs, we use the heap, not use the stack, because we always require a lot of data. Like this kind of simulation like requires what, around millions of particles if you are going to simulate like a big problem. So million of particles, you can multiply it by these parameters. Like you need a lot of memory. So we define it in the heap usually. And for sure, whenever you use the heap memory, you need to manage the memory properly. So make sure that you delete before exiting the program. So what else we're gonna create? We still in the particle.cpp file, and we're gonna create a setter methods that just take vectors, and it's used for initiating this arrays. So just when I call this method, it will take the input vectors. Whenever I call this method from my program, it will take the data and initialize these class parameters. So let's now go to the main. Now we are in the main function. So we started by the data type. After that, we define a class that will help us. Now let's go to the core of the program. So what you can see at the beginning, it is just a Linux command, because, or you can modify it to work in Windows, but we are using Linux, open source software, open source operating system. So we just wanted to create a folder for the results that will hold like store, where we can store our files, our results over the time in it. So this is just for creating and saving folder if it does not exist. And what you can see here, it is just initializing the problem domain, like what is the X direction, what is the Y direction, what is the Z direction, what is the dimension in each direction. Like we in the presentation, we mentioned that we gonna use 10 centimeters, so we are using metrics. We use meters, so 0.1 meters in every direction. And we're gonna specify, okay, what is the delta X, delta Y, and delta Z? Like what is the spacing? What is the spacing between the particles? And lastly, how many, okay, so from these data, we can calculate how many particles in the X and Y and Z direction. And the last thing here, it is something called smoothing lens factor, which is something we will discuss it later. But this is just a constant factor. We need it, and we will discuss it later. So after that, we created like the particles, like we created the particles, like an instance from the class, and we will initialize it. So in order to just to make the main function doesn't have a lot of code, so we created another function that is responsible for initializing the particles. And here you can see the first thing, we have these like constant. What is the thermal conductivity? What is the specific heat? What is the density? What is the mass? What is something parameter called H? What is the initial temperature? What is the boundary temperature? So these are just constants, and we created a vectors that will hold these data, and we just iterated in the X and Y and Z direction for every point in the domain, and initialize it with these parameter, like with its position, with the thermal conductivity, with the density, and so on. And the last thing, okay, so now everything is ready. I can just call the setter method, so it can take this data and set the parameter of the particle. So by the end of this method, we have initialized the particle, like every particle know what its density, what its initial temperature, what its position, and so on. So let's go back to the main. And so what we did, we initialized the problem, and here we initialize the domain, and now we are done with initializing the particles. So what else? We need to run the simulation. We need to run the simulation itself. So run simulation, it is a function that consists of three main methods. So writing a VTK file, interactions between the particles, and update through the time. So let's take it down step by step. So writing a VTK file. So you can see here, we at the beginning of running a simulation, we write like the initial state of the problem, and through the time, what is this for loop? We are iterating over the 10 seconds because we need to see the solution over the 10 second, like in every time step delta t that we will specify. Okay, we need to know what is the solution now. So you can see here we are writing the file. So in order to visualize, because we have the data, now we know we have these points that have the thermal properties and it has the temperature, how we can see, visualize it. So one of the solutions is to use a VTK file. VTK file, it's just a CSV file, like a file that has a certain format. So we can write functions that print this format in a file, so we can read it and or visualize it. So this, like this method, if you have a look here. So the first thing, okay, so I'm going to save in the results folder that I created in the beginning of the main, and at time step or at a step that I'm going to pass. So at every step, we're gonna save the file that represented, okay, what is the state of the problem now? And you can see here, like here, this is the particle's position, and this is how we need to print it, and this is the particle temperatures. So what else is here? It is just the format, the structure. If you are interested, you can just go to VTK format and you will find, okay, it must begin with something called the name and what is the data you are using, and after that new line. So it is just formatting the file as you need. What else? So this function at the end will print the file in the results folder. So what you can do, okay, we have the results in file, just go to this folder, like drag and drop it in ParaView program, and you will see the result ready to be visualized. And this ParaView, you can download it. It is open source program, free to use, and you can see the results over the time, because this file, you can specify this is the result over the time. So let's go back. So we are in the running simulation method, and now we understand these two methods, or this method about writing the VTK or writing the results to the file. So what else? We have the method called interaction. So what is the interaction? It's simply, okay, how the heat is transferred from particles to another particles. You can again imagine it like if you are sitting away from a heater, so you have a less effect of the heat. And if you are close, you will have more heat. So this is the same thing. So if a particle I, close to it, many hot particles J, this temperature will arise. And how far the particle J will affect particle I, it is a function of this gradient, which is just a weight. How this weight is represented? Like how this weight is represented, it is just represented by this function called psi function. Psi. There are many like research field about what is the good functions that can represent, but let's understand what is happening here. Like if I have a particle I, this is the red one, and so I'm gonna go through all the particles and define particles of neighbors. So particles of neighbors, they are the green one. So like in a certain radius, outside this certain radius, I don't take care of them, like they are out of my concern. And so inside the green ones, what I do, if the particle is close to the red, its value will, like its effect will be huge. But as far as I go, the effect of it, it's gonna be low or small. So this is the idea of heat exchange. So yes, I'm gonna iterate through all these particles, and as depend on the distance, I will have a weight of it. If the distance is far away, so okay, I have a less weight, I have a less effect over the red particles. So how we can do it programmingly? So we are now in the interaction.cpp file or interaction heat function. So first thing, okay, because the particle from the equation, you can see I have the red one, which is represented by I, which is Ti, Ki, CVPI, rho I. So we need to get this information about particle I now. So, and this particle I will be all the particles. So this is why I need a for loop to iterate through all the particles. And this red point will be changed like in every iteration. Like I will go through all the points in the domain. And for every point in this iteration, I will need to grab the information. Why? Because I'm gonna use it in this equation that is describes the system. So this is the particle I. So it's gonna interact with the greens one. So I need another for loop that's gonna iterate through the domain, and based on the properties of these particles and how far it is, it will affect the I. So this is another for loop, which represents the J, which is the green one here. And so I'm grabbing the data information about it. And at the end, I'm calculating T of I, or a change of temperature, the change of the temperature. So you can see here, we calculated this like 4 Ki Kj, 4 Ki Kj, and multiplied by this weight, which is the function, like this function. And this function, it's written in another file. We will discuss it later. But at the end, you will have it. So what is missing here is this Laplace equation or psi equation. So the psi equation, if you just search it, it is just an equation depend on how far, again, how far the particles, uh, how far they are away from each other. So if a particle is close, so you will have a high value, and if it is particle is like far away, you will have a less value. And this equation, you can just search about it, and there are many equations, but this is just a simplification about what this psi equation. You can just write SCBH psi equation, and you will have like many versions of it. But this is one, it is used and validated in many researches. So let's go back to run simulation. So run simulation, we now know what is how to write our results, how the particles are interacting in this time step. So remember, we are in this for loop, like we're gonna iterate through this 10 seconds in simple, very small time steps. So I wanted to update the states in every time step. So that is why we have this method called update, and it's simply, okay, it calculated what is the temperature in the previous step. Okay, it will be equal to what is my temperature in the previous step plus the change through the time. So this is the update of the state of the problem. So that's it. So now we have all the codes or the equations or the implementation of the ideas that make our program works. So how it works, like you can notice that I wrote in some files, I structured my program in a certain file structure, so we can compile our code using or build it using CMake. CMake just, it is a tool, open source tool that allows to multi-files building. It makes the work easier. So this is just a CMake. And you can find the instruction about how to build it and how to run it, which we'll do it now together in the GitHub repository, which you will find the link at the end of this presentation. So at the end, you will have at the end, after running the program, you will have, okay, this is the change of the temperature over the time of 10 seconds. So let's now exit the presentation and go to the code to show you how the file is structured. So again, we have, this is the file or the folder for the project. You can clone it from a GitHub repository. And we have the include directory and source, which includes the .cpp. We have the main function, and you will notice it is the same thing that we discussed. It has the main function that initializing the problem, and we have the run simulation, and we have this class particle.h, which contains the data, and particles.cpp, which include initializing, particle.cpp, initializing and the memory, and initializing the properties, and deleting the memory at the end. So how we can build it? So like you have just cloned the project. Like now you need to create, let me delete the build directory. So this is like, now you cloned it. So the first thing you need to make directory called build. After that, cd build to change directory. After that, cmake space dot dot. After that, make. So the project is built, compiled successfully. We can run it by using ./sh, and we can start running it. So now it's running, and it will print like every 1% of completion. Okay, we finished 1% and we saved the file. It is running now, so percentage of completion 1. So if we open here the results folder, so you will see that it is coming. The files, the solutions over the time is coming. So 2%, let's wait 1 more percent, 3%, the solution is coming, and so on. So we can close it now because I already ran the program before our webinar. So these are the results. So how we can visualize? So this file, if you open it, like let's open it by text file, like it's just a text file. So like it has a certain, you can see it has a certain format. So how can we read this data? We can just like drag, like mark them all, drag and drop them in ParaView, the programs that I open source program. So I can just change, I wanted to set as a point, and let's make the size of points. Okay, bigger. So this is our problem, and that's it. Just the coloring. And yes, ParaView, it's just 5 minutes tutorial about how to use it. You will understand it easily without a problem. So we can run the simulation or show, not run the simulation, show the results over the time. So as you can see now, it is now like you can see the results over the time. So we can play it again. So what you have just saw, it is already, let's go back to the slide. So what we discussed, it is actually what is happening in any big like solver or programs. Exactly, they are building their solver like what we are doing now. So let's recap and summarize what we did. So again, we began from where we began by going back to the data type. Okay, which data type we wanted to use? Okay, let's make our program as a generic one so we can switch between data type easily without a problem. And what next we did? So we created our particles, like initializing it, where is they are located, what is the problem dimensions, and setting the properties. And after that, we run the simulation. And the run simulation function contains 3 main things: just the interaction between the particles, how the heat is transformed, because it is a thermal heat. Later, how the stresses is, like particles are interacted, the stresses are affected due to the change of the positions of the particles for other simulations. And we update over the time, and we save our files, our results in a folder. So that's it. So what is next? So yes, like the good thing about this science or this topic, it is scalable. Like you can build a layer and another one can build another layer, and you can remove this layer, insert another layer. So it is a big room for developing. So what is next? Maybe yes, you can include another properties like material properties to the solver, and also you can speed it up. Like you can notice that we did here 2 for loops. So this is a lot of processing. Like imagine you have 1 million particles, so you're gonna iterate 1 million by 1 million particles, like trillions of iterations, which is too much. So how we can solve it? There are many solutions for this, like using hashing. Hashing, it is a big topic in computer science, but it make it fast actually. It is idea about dividing the domain into subdomains. So hashing, if you just search about it, it is a big topic and it's applicable here and it speeds up actually the problem or the solver. And using multi-threading, using GPGPU programming, which are what I'm doing now in my research, or apply them all. So that was it. As I said, you will find some good papers and about this science, and you will find a link for the solver. In the first link, it's just the link for the solver that we developed, or the program that we developed today. So I'm done and I'm ready for your questions.
Good. Thank you so much, Ahmed. Folks, if you have any questions, please put them in the Q&A tab. We have sufficient time. Ahmed can take questions. As of now, Ahmed, I see just one question in the Q&A tab, and I'll read it out to you. It
Yes.
is, what is the benefit of this topic, or where can we use this? Where can we see this, and when can we do this simulation?
Okay, where we can first, what is the benefit of this topic? If you came from a research field, it will help a lot. If you are working in a research, developing new ideas, developing a new theory, so this is a big room for it. And another thing, it is the companies that is working on simulation. There are many open positions, and unfortunately, like to find someone who understands what is happening, like if you just applied for the job and you know what is happening behind the scenes, so you have a big advantage to be selected. And where why we use simulations? Actually, for many reasons, actually saving time, money, effort, saving money. If you want to understand something, you will go to the lab to study it, or not only for science, like for big factories like Airbus doing a lot of simulations to train their pilots. This is a kind of simulation to study how the flow of the air around the plane, what is the stresses when the temperature of the engine increases, what is its effect on the body of the vehicle, whatever it is the vehicle, it's a flight or something else it is. So there are like everyone is using the simulation regarding to manufacturing, regarding to research, regarding to development. So it is used everywhere almost.
Got it. Hopefully, Amani, that answers your question. If you have follow-ups, feel free to post them. The next question comes from Bhanvi. She asks, how can we integrate AI in this? And can you tell me how to run this code after cloning it?
Okay. So how we can integrate AI in this? Actually, there are a topic now which combine like physics-informed neural network. Physics-informed neural network, it depends on, okay, you have a data that came from laboratory, but usually this data is not like enough, because, okay, you will do just one experiment, you will have 1 to 10, 100 sets of data, which is not enough for training your model. So what we do the lab work, have hundreds of sets of data, and after that we start to run simulations, like thousands of simulations, so we can combine these data and building our data set, so we can train our model. So physics-informed neural network, it is one of the big fields that can incorporate simulation with data and build your model. And about running the code, you will find the instruction in the GitHub repository about like step by step how to clone and run it on your computer.
Got it. Awesome. Derek, I see you've raised your hand. Unfortunately, we will not be able to unmute you to speak. If you have any questions, please feel free to post it in the Q&A. We'll be sure to take that up. I see one more question here. Do we have courses on simulation? I believe that's a Udacity question. I'll get back to you on that. Very honestly, I manage the School of Business, so this is a little outside my area of expertise as well. We've got my colleagues who handle this particular school, and they can sort of advise you on this. What I would recommend you to do is we have a form at the end of Ahmed's presentation. Please just drop this question in that form. And what we'll do is we'll get back to you early next week with our recommendations about the courses. The next question is, where can we see this recording so we can refer to it anytime? So this session is being recorded. We do plan to use it for our channels like YouTube. However, there's no publishing schedule out as just yet. So just be subscribed to the YouTube channel and you'll probably see the recording out there. We have a question coming in from Christopher Phillips, and the question is Linux preferred for simulations?
Linux is preferred for developing like open source. It is open source, so you can handle everything easily, but it's still you can use Windows, any operating system. But maybe if I can advise you, if you're gonna work in this field or developing codes, whatever this codes about simulation or anything, you may need to check Linux or learn a Linux operating system.
Got it. We have a question from Andre. I'm not exactly sure if this is clear, but I'll just read it out. Your website mentions applications in the US Department of Energy, but without examples. Can you provide examples of possible applications in electric power systems?
I have no idea, actually.
Yeah, we'll need some more context around this, Andre. Feel free to fill up that form, and we can take this question offline. We'll try to address any doubts you have, but we'll need to take this offline. Yeah, those are all the questions I see at the moment. So yeah, I think we've answered everything that's come up. All right. If we weren't able to address any of your questions, as I already said a few minutes earlier, just put it in the Google form linked at the end of Ahmed's presentation, and we'll get back to you early next week. And we'll do our best to provide whatever guidance we can. To just conclude the session, thank you all for attending. We are concluding the pilot of this webinar series. However, we do intend to make this a regular feature, so we'll be back in March. And if you would like to join us for future topics, you're most welcome to do so. We have some couple of very interesting topics that we're keen to pick up. One is agentic AI. The other is around meta ads, how to create effective meta ads. So a lot of interesting topics from a lot of different schools that we plan to pick up in this webinar series when we resume. So please just keep an eye on your emails. We send out email communication usually a week before the event date. So just keep an eye on your emails and you'll be able to join in. Before we go, we'd love your feedback on today's session. So when you log out, a small pop-up would appear in your browser after you exit the call. And it's a very short form. It's just a couple of multiple choice questions. So it should take you just a very short amount of time. And there's one optional open-ended question if you'd like to share your thoughts. Your feedback will be of great help to help us refine the future sessions. And with that, we'll take your leave and we wish you a happy weekend. Take care. And, see you soon.